So now I'm going to give you an introduction to analysis of variance, or ANOVA. There won't be any math in this video, I'm just going to talk about what ANOVA is. I'm going to touch on these topics. First, an introduction to ANOVA, then the different types of ANOVA, the assumptions of ANOVA, how you form hypotheses in ANOVA, what main effects and interaction effects are, what post hoc tests are, and what the F distribution is. So first of all, ANOVA. ANOVA is a statistical method used to compare the means of two or more groups. Like before, when we were doing t-tests, we could compare two samples. With ANOVA, we can compare 3 samples, or 4 samples, or 7 samples. We can compare more than 2 groups. Now in ANOVA, you have factors and you have levels. Factors are just your variables, like in one case, gender could be a factor, and levels are the levels of those variables. Like gender could have 2 levels, male and female. So like here's an example with 3 groups, 0 milligram, 50 milligram, and 100 milligram. Those are different dosages. So in this case, your factor is dosage, and your dosage factor has 3 levels, 0, 50, and 100. Now there are a few different types of ANOVA, and I'm going to show you about 3 right here. I'm going to show you first the one-way ANOVA. This is an ANOVA that has one factor with at least 2 levels, and the levels are independent. There's also the repeated measures ANOVA. This is one factor with at least 2 levels, but the levels are dependent. Like now you can see the data has changed. We're measuring the same people, day 1, day 2, and day 3. It looks almost exactly the same, but now we're dealing with dependent data. So make sure you know the difference between independent data and dependent data. I actually have a separate lecture on that if you want to check that out. There's also a factorial ANOVA. Now a factorial ANOVA has 2 or more factors, and each of those factors have at least 2 levels. The levels can be either independent, dependent, or both. If they're both, it's called a mixed factorial design. So here's a design that has 2 variables. One is gender, men and women, and one is day. You have day 1, day 2, day 3. So that's 2 factors. One has 2 levels and one has 3 levels. That's a factorial ANOVA. Now ANOVA has a few assumptions. The first assumption is normality of sampling distribution of means, meaning that the distribution of sample means is normally distributed. We pretty much always assume this is true, and it's usually not a problem. The second is independence of errors, that error between cases are independent of one another. The third is absence of outliers. Outlying scores have to be removed from the dataset if you would like to perform an ANOVA and get a meaningful result. And the fourth is homogeneity of variance, or homogeny, or however you say it. Population variances in different levels of each independent variable are equal. And there's actually a special test for that, which I won't do now, but we'll do it when we start doing ANOVAs. Now, hypotheses in ANOVA. Imagine you have one factor with 3 levels. Your null hypothesis is that all 3 levels are equal to one another. Your alternative is that not all means are equal. Now, you can't write A1 is not equal to A2 is not equal to A3, because that would imply that all 3 means are different. Maybe only 1 and 2 are different, and maybe only 1 and 3 are different. So your alternative has to be written as not all means are equal. When you're dealing with the effect of one variable, it's called a main effect. But here, imagine we have an ANOVA with 2 factors, A and B. You would have 3 different sets of hypotheses. You'd have one for A, one for B, and one for the combination, or the interaction of A and B. And if you had 3 factors, you'd have even more things going on. So here you have the main effect of A and the main effect of B, and you can also test for the interaction of A and B, which would be structured just like that, the null being the interaction is absent, and the alternative being that the interaction is present. So let me talk a little bit more about that. First of all, main effects. Pretend we're comparing the test scores of people who have received a medication in the 100 milligram dosage group, and people who have not received the medication in the 0 milligram dosage group. The 0 milligram condition has a mean of 60, while the 100 milligram condition has a mean of 80. This could be represented in a graph like this. This would be a main effect. The first group has a mean of 60, and the second group has a mean of 80. This is how you could draw it in a graph. And I'm doing it like this because it's a little bit more meaningful. It's a more meaningful way of showing an interaction in ANOVA. So here's an interaction. Let's say we have a factorial ANOVA with 2 factors. We have dosage, and now we have gender, men and women. So in the 0 milligram dosage condition, men have a mean of 60 while women have a mean of 80. In the 100 milligram dosage condition, men have a mean of 80 while women have a mean of 50. So now the graph would look something like this. You can see that the lines for men and women cross. If the lines cross like this, that means you have an interaction effect in your ANOVA. Basically, what an interaction means is that the effect at one level depends on the other level. So for example, at 0 milligram, men are lower than women, but at 100 milligrams, men are higher than women. So really the effect of gender depends on what level of dosage you're at, and the effect of dosage depends on what level of gender you're at. The variables have interacted in this way, and that's what it means for there to be an interaction effect in your ANOVA. Now after you do an ANOVA, you might do something called a post hoc analysis. Because remember, if we reject the null hypothesis, all we know is that there is a difference somewhere between our groups. We don't know where that difference is. So additional tests called post hoc tests can be done to help determine where the differences lie. Maybe groups 1 and 2 are different, maybe 2 and 3 are different, maybe they're all different. The post hoc test will tell us that, and there are several different ones we can perform. And of course we have the F distribution. When doing an ANOVA, we calculate an F statistic. It is similar to the other statistics I've talked about so far, like the Z and the T. F is at its most basic form like this. It is treatment differences plus random differences divided by random differences. If there are no treatment differences, that is, if there's no actual effect, if there's really no real difference between the groups, we would expect F to be 1. If there are treatment differences, we expect F to be greater than 1. The F statistic has its own one-tailed distribution, much like how the Z and the T statistics have their own separate distributions. So the F distribution is always one-tailed, and our F is always going to be positive. If you get a negative F, that means you made some kind of mistake. And that's it. There's no math here. That's just the basic introduction to what ANOVA is and how we're going to be using it in the future.